this Max tutorial, we will implement a pitch shifter using a delay line in Gen. So before we start implementing this time domain delay line pitch shifter, let's maybe quickly go over what we're trying to achieve here. So the main idea is that we will continuously write audio into a circular buffer and then read it back at a slightly different speed. So if the reading back is faster, then the pitch goes up, and if the reading back is slower, then the pitch goes down. And because the reading pointer has to wrap around periodically, we will be using two overlapping reading heads and a windowed crossfade function that will always fade in and fade out the playback. So you can think of this as like an infinite tape loop, where we have a writing head that constantly writes audio onto this loop, and two reading heads that constantly read it, but they're also moving in a defined region behind this writing head. Because they're moving and looping, these two reading heads, we need to have a window function, so when they jump back to the start position of this region, this won't cause any clicks. So I first came across this idea in the book The Theory and Technique of Electronic Music by Miller Puckett. I will put a link into the description so you can have a look yourself. Okay, so this tutorial consists of 5 parts. In the first one, we will create a window. In the second one, we will implement the circular recording buffer. In the third one, we will look into how we can get the right pitch ratio, so we can shift it up and down a defined number of semitones. In the fourth one, we will implement 2 reading heads, and in the fifth one, we will then apply this window function to our reading heads. Okay, I am starting off with a sound file. I have a live gain and an easy DAC so we can hear what we're doing. Okay, starting off with the window function. First, I will create a buffer to read from. Let's call this one window, and let's define its size in terms of samples. So let's say we have 1,000 samples here. So in order to fill this buffer, I will use a gen codebox object. So not gen tilde, but just regular gen, because with this we can also access this buffer. But I think first I will also use a waveform object so we can see what's inside this buffer. In order to assign this, we can say set and then the name of the buffer. And now we can see the contents of this buffer in here, which is now, of course, empty because we didn't fill it yet. Okay, in order to access this buffer in our gen codebox, we need to use the same name as we did here. So we can say buffer window. Then, so I want to fill this buffer with a for loop. So going over all of the samples we have in here. And in order to trigger this, I will create a variable, call this one trigger. This is input 1. So that if I'm sending a message 1 in our first inlet, this will be triggered. So we can say if trigger, so it checks if trigger is 1. Then we want to fill our buffer. Okay. Then, as I said, we want to iterate over all of the samples. But first I will check I got an error here. Patch code. Oh, I see what's happening here. So this one is complaining because we don't have an outlet. I mean, technically we don't need one in here, but I will just define an outlet so we will get rid of this error. Okay. Where were we? Yeah, the for loop. So I want to iterate over all of our samples. So we can say for I equals 0 and I smaller than the dimension of our buffer. And this dimension is given in the number of samples. And then we need to increment, so I plus, plus equals 1. Okay, so I will first define a normalized index. So I want to fill this buffer with samples that range from 0 to 1. So to do this, I can just say norm index equals, then I take I, so this one will go from 0 to 1000 in this case. And if we're dividing this just by the size, we will start by 0 divided by 1000 up to 1000 divided by 1000, which will be 1. And then we also have to fill the buffer with this just to see if it's working. So to fill a buffer, we can use the poke function. There we first define, okay, this is the buffer we want to fill. Then we need to specify the value and then also the index. So this means that for the buffer window at this index, we want to have this value. And to make it explicit, I will say index equals samples. So we're not using a normalized index, but we're going sample by sample. Okay. And if I didn't make any mistake, we could just send in the 1 here and then this one will fill. Perfect. So this is what I wanted. But yeah, I don't want to have this normalized index. I want to have a smooth fade in and a smooth fade out here for our window function. So let's maybe say fade equals, and then I want to use this to drive a sine function. So I can say sine norm index times pi. So now we'll have a number ranging from 0 to pi, and we plug this into our sine function. And so a full sine function would be 0 to 2 pi, but I only want half of the sine function because I only want a fade in and a fade out and not the full waveform. So theoretically, if we then say we don't want the norm index here, but the fade, yeah, we have a fade in and a fade out. But I think I also want to apply an exponent here. So let's say power fade 0.5, sorry. And this essentially means that we will have an emphasis on the lower values. So the lower values will be stretched upwards. So if I apply this, you can see that the fade in is a bit faster. Yeah, I will leave it like this for now. We can later take a listen and see if we're satisfied with how this sounds or if we want to change it. But for now, I think we're good with this. And in order to initialize this, we could also just say load mass 1. So on startup, we're sending a 1 in here. Okay, that's it for the first part. Now let's move on to the second part, which will be the circular recording buffer. In order to implement this, I will create a gen codebox tilde. And I think the rest of the code will just live in here. Okay, I will make some space because we're going to need it later on. So I will connect the audio here and I connect the output to our live gain so we can hear what's going on. Yeah, for the circular recording buffer, first I will create another buffer. So I can just duplicate this one. Let's maybe call this one audio buffer. And now I don't want to define this in terms of samples, but in terms of milliseconds. So this one should be 100 milliseconds. And then we can do the same down here as we did with the window buffer. Okay. Now, same thing again here. We can assign this buffer inside of our gen. So we can say buffer audio buffer. And yeah, if we have the same name as we do here, this one will essentially be the same buffer. Okay, so then I want to define a variable called buffer size, because I think we're going to need this quite a lot. And buffer size is the dimension of our audio buffer. So again, this is the number of samples that we have in here. Okay. Then maybe, yeah, use comments. So we want to write to the buffer. So in order to do this, first I want a writing position. So let's call this write pause. And this is, so we can use, so the idea is that we want to have a circular buffer. So when we reach the end of the buffer, we want to start over again. So in order to do this, we can use the wrap function and the elapsed variable and say between 0 and buffer size. And what this is going to do is, so elapsed is a built-in variable that starts at 0 when you turn on audio or when you initialize the patch. And then it just increments by 1 for each sample. So if our sampling rate is 48 kilohertz, then for every second, this will add 48,000. But we want to wrap this thing around when we reach the end of our buffer size. So we can just say wrap between 0 and the buffer size. And then we'll have essentially for each sample, we're counting, or for the length of the buffer, we're counting the number of samples of the buffer. And then we can do something like, using the poke function, like we did here again, and say, first we have to define the buffer we want to poke. Then we have to define the value. So the value will just be the incoming samples of our audio file we have here. And the writing position will be this here. And then also to make it explicit, we can say index equals samples. And I got an error again. But I think, yeah, it's essentially the same we got here, because this one wants an output, so we can just say out is 0 for now. And theoretically, if we play this, yeah, you can see that we're writing into this buffer. And because it's very short, it's not clear, I think, that it's a circular buffer. So maybe if we say this one is 2 seconds long, it should be more explicit. So now you can see parts of the audio continuously get overwritten. Okay, let's change this back to 100 milliseconds. So I think now we can come to the third part, the pitch ratio. And what I want to do here is, so I want to define a parameter. Let's call this pitch ratio. Set it to 0 for now. And the idea is that I want to define this in terms of semitones. So if this one is 0, I don't want to shift the pitch. If this one is 1, I want a pitch shift of 1 semitone. If this one is 12, it should be 12 semitones, so 1 octave. If this one is minus 12, it should be pitched down 1 octave. So in order to do this, I want to define this, or I want to get to this in terms of the ratio between two frequencies. I'm going to show you what I mean by that. So let's put this one here. And then we can say pitch equals MIDI to frequency. So this one takes in a MIDI note and spits out a frequency. Here we can plug in our pitch ratio. So now this one is 0, so it will give us the MIDI note for 0, or it will give us the frequency for the MIDI note 0. Then we can use this one, which is just 0. So if this one is 0 and this one is 0, so it's some frequency divided by the same frequency, which will give us 1. And if this one is 12 and this one is 0, then it's the difference of 1 octave. So this will give us 1/2. So the pitch is, no, not 1/2, it will give us 2. So this is essentially a way for us to plug in semitones and get out the correct ratio in terms of pitches. But I can't leave it like that, because here this is, so if this one is 0, we will get out a 1, but I want it to be 0 if it's the same, so we can just say -1 here. So maybe let's take a quick look what this actually means. So I will create another output so we can quickly check if this is working. So here I can use pitch ratio. Now it's 0. If I go to 1, so this is 1 semitone. So if I go to 12, this should be 2. No, of course, now it's 1 because I have -1 here. Yeah. -12 is -0.5. Okay. Yeah, that's essentially what we want. Setting this back to 0, then we can get rid of this. Because this will then be used to drive the playback, and an octave is double the speed, shifting down an octave is half the speed, and everything in between, where I'm obviously not sure which ratios we have. Okay, so that's it for the third part, the pitch ratio. Now we can go to the fun part, the two reading heads. So first I will create a phase that goes from 0 to 1. So we can control the speed of the playback heads. So phase equals, now I will use the accum function. So this one accumulates whatever the argument is per sample. So if this is 1, then we will increment by 1 on every sample. So this is essentially the same as our elapsed here. But we don't want to increment by 1, but we want to take the length of the region that we're reading from into account. As I said before, we will define a region behind the right head, so to say, so behind the right position, that's a certain size, and within that region we want to loop the audio at a specific speed. So in order to do this, I will also create a parameter, let's call this one grain size ms. So this is the, I mean, it's not really, I'm not sure if grain is the right word. Let's call this maybe read size in milliseconds. And as the name suggests, I want to define this in terms of milliseconds. So let's say this region has a length of 10 milliseconds. And then here we can say 1 divided by, no, first we need to get from milliseconds to samples. So let's say read size samples to be explicit, and then we can use ms to samps. So this takes milliseconds as an input and gives us the number of samples at the current sampling rate, of course, as an output. And if we do this, then essentially what we're getting is a ramp from 0 to 1 that takes exactly the time specified here. So now we get a ramp from 0 to 1 that lasts 10 milliseconds. But the problem is that this will just accumulate on forever. So we have to say phase equals wrap of phase, and then we can wrap it between 0 and 1. But now this one will always have the same speed, and the speed in this case refers also to the pitch. So if we want to change this in terms of our pitch, we have to say not 1 divided by the size in samples, but we have to use the pitch to divide the size in samples. So as I said, if this is an octave, this will be 2, so it will have twice the speed. If this one is shifted down by an octave, it's 1/2, so it's 1/2 the speed. So this is how we can control the speed, and yeah, with this wrap, it stays between 0 and 1. Okay, then I want to define the position of our reading region, so to say. So we can say read pause. So we can define this variable called read pause. And we'll have 2 of them because we have 2 reading heads. So read pause 1 equals, it's just the phase multiplied by the read size in samples. So now we have the position in terms of actual samples. And the second reading head is always half a region ahead of this. So if you can imagine, if this is 10 milliseconds behind the writing head, the first reading head starts at 0 and the second one starts at 0.5, and then one is always fading in while the other one is fading out. But in order to put this on a different position, we can again use the wrap function and say that we want to wrap the phase between 0 and 1, but we'll always add 0.5. So this will start at 0, this will start at 0.5, and then, of course, again, we multiply this so we get the actual position in terms of samples. But we're not done here, because we also have to take the writing position into account. Now this will start at 0 and this will start at half of the read size, but this should always be the size of the reading region behind the writing position. Okay, I guess this was a bit complicated, so I will just show you what I mean. So again, I'm saying read position equals the write position. So this is where the write head is, where we're creating new audio in our buffer. Then minus the size of our region. So imagine that this is at sample 1000 and the size of our region is whatever, 100 samples. Then this means that we're essentially starting at 1000 minus 100 samples, so at 900 samples, plus this thing, which will be minimum 0 and maximum the read size in samples. So essentially this means that we defined the region here, and here we're moving through our region. But as you can see, this writing position is always changing, so we need to be careful and also wrap this, because it will go over the number of actual samples we have in the buffer. So we can say something like wrap between 0 and our buffer size. And then we can do the exact same thing for our read position 2. We don't have to change anything except for using read position 2 here. And then, yeah, again, this is the region, this is the actual position, and here we're checking that we're not going over the buffer size. Okay. Then I want to convert this back to a phase, so to a number between 0 and 1. Let's call this read phase is, okay, first read phase is this divided by our buffer size. So this will give us the phase as a number between 0 and 1, and of course we also need this one twice for our second reading head. Then, yeah, now we can use it to create the actual signal. So the first signal is then, so here we used poke in order to write into a buffer. In order to read from a buffer, we can use peak. Here we also have to define the buffer we want to read from. Then we want to define the phase we want to use. And because we're using a phase here, we have to say index equals phase. So here we use the index samples, which means that with the right position, we're using the actual sample index. And here with index phase, we're using a ramp between 0 and 1, which essentially is this here. And I will also say I want to use interpolation. Then I can just copy this thing here. Say signal 2. Then we can use the read phase 2, which is at a different position. And then I think we're almost done now. We can now come to the fifth and final part, implementing the window. But I think I'm running out of space, so I will put this one here. And then we can get some more space down here. So final part, implementing the window function. So because we have two signals, we also need two windows, or let's call it fade. So fade 1 equals, again, we're using the peak function, but this time, okay, I have to define the window buffer up here so we can use it, same as with the other buffer. So let's say buffer window. So again, same name. So we are referring to the same buffer. So I can say peak window. Then I can, wait. So this one is between 0 and 1, but it's always, so this is just the region behind. So I can just use this phase because this phase goes over the whole thing. Yeah. So we're using this phase. And then I can copy all of this. Because index should be phase again, because we're using a number between 0 and 1. Then I can copy the whole thing for our second fade, but here, yeah, we need to change the phase because this one needs to be, so the second one as with this one here. So this starts at 0.5. So I guess we can just copy the whole thing here and say phase plus 0.5, wrap it between 0 and 1, because then this is just shifted by half the phase. I will make some more space. I just got an error. Okay. I'm missing the semicolon here. Okay. So now we have the window, we have the final signal, and here we can combine them. We can say signal 1 plus fade 1. No, not plus, we have to multiply this. So signal 1 will fade in and fade out according to this window. And then we can add signal 2 plus fade 2. And yeah, every time signal 1 is at a maximum here according to this window, signal 2 will be at the minimum because they're shifted by half the window size and vice versa. So I got another error. Okay, because I also forgot it here. So in theory, if I didn't make any mistakes, this should be working now. Let's hear. Okay, now we can hear no shifting. Then let's shift it up by 1 semitone. This one has to be a multiplication. Okay, now going up to 1 octave. Okay, yeah, and the thing is with this kind of pitch shifting, there's always a trade-off between having a larger buffer size or a larger region size, which gives a smoother, more stable pitch shifting, but it will increase the latency. But smaller regions will cause more artifacts because we have to read through this window and this overlap more often. I mean, we can also, you can see what happens if we use like 5. Yeah, you can hear how the quality changes. Or maybe use 1 second. Yeah, so you can try out different values, see what suits you best. This is by no means the perfect pitch shifting algorithm. It's just, yeah, a very interesting technique that I wanted to work with. So yeah, this is essentially what I wanted to show you. I hope you found this useful. Thanks for watching.